so I want to finish construction of this asymptotic space and discuss what can be done next. So we have a parabolic space or parabolic plane or Lobachevsky plane. So I use polar coordinates. This is rho, and this is, say, phi. And H is parabolic plane. H is a parabolic plane. Now I consider the non-standard extension of all this. So star H, star rho, star phi, the same object in the extended universe. So we extended our universe and uniquely embedded our objects into the extended universe. So in particular, rho in star R plus and phi in star 0 to pi. So we add here some new elements which is important. And here is the origin O, which is the same in both universes. Now I remind you the formula for the distance in the standard universe, which we will already in non-standard universe. If you have 2 points, x1 equals rho 1 phi 1, x2 equals rho 2 phi 2, x1 x2 in star H. So these 2 points. Then we more or less derive the following formula. One moment. Of course, I introduce d epsilon of xy equals epsilon times d of xy, epsilon in star R plus epsilon is infinitesimal. The epsilon is epsilon times this. So I write standard part of the epsilon between xy equals standard part of the following thing. Epsilon logarithm, let me write this, e to the power rho 1 minus rho 2 plus beta square e to the power rho 1 plus rho 2. So here beta square equals 1 minus cosine phi1 minus phi2. No, we are interested in case when phi1 minus phi2 is infinitesimal, so we can write after all, so we can replace this by 1 minus 1/2 phi1 minus phi2 square. And so standard part start the epsilon between xy equals standard part of maximum of epsilon times rho 1 minus rho 2 epsilon times maximum of 2 epsilon rho 1 minus rho 2 epsilon times rho 1 plus rho 2 minus 2 phi. So what is phi? Capital phi1 minus phi2 is denoted by e to the power minus phi. Yeah. No, why so? Because here you have epsilon times logarithm of sum of two exponents. Yeah, and exponents are very stiff function. So and logarithm as is very soft. So if these exponents go up are high, then one of them is much more than other, and so logarithm will fill only the one which is larger. So therefore it chooses either this or this. If you consider standard setup, then there is some error, and in this non-standard it is much stiffer, so the standard part takes care of erasing all the errors which are here. So this is our formula for the distance. It looks quite simple, and let me explain the geometric picture which is behind this formula. So if you have 2 points x1 and x2, and they are far away, so the distance is large from O, then the picture in the hyperbolic plane looks as follows: that the geodesics from O to x1 and from O to x2 goes sometime very close to one another, And then they all of a sudden diverge like this. Yeah, so this is the typical picture in the hyperbolic plane. So the distance between these geodesics grows exponential, no, in fact, like hyperbolic sine, some small coefficient in front of it. So for some time it is really small, but this exponential growth prevails here, and they suddenly diverge. So no, suddenly here they look like graphs of exponent. But if you now multiply everything by epsilon, so you shrink it, then you will have this limit picture is this. Yes, and x2. Yeah, this means that you have to go some distance here and then go here. And the geodesic which goes from x1 to x2 looks quite similar. It goes like this. So part goes practically along this first geodesic, part along the second geodesic, and here is some small, relatively small transition domain. So this first term becomes maximal if these 2 points, x1 and x2, are more or less on the same line. So it is O, it is x1, it is x2. Then the distance is simply epsilon times ρ1 minus ρ2. Otherwise, we have this picture, so they diverge at some distance from x1 and x2, and this is yes, and it's reflected by this phi. Okay, and then now how can you extract this picture from our formulas? So let me remind you what was last time about the decomposition of non-standard numbers. So suppose we have non-standard numbers. Start R plus, so we consider just positive numbers. Then I remind you, we write x is equivalent to y if x over y less than k and y over x less than k for some standard positive k. So they are of the same order. So this is equivalence relation, and we denoted by lambda is start R factor over this equivalence relation. Now these elements is lambda elements of this set. And if x in lambda, we write lambda equals lambda of x. Now we chose in each of the class lambda, we take a lambda in each lambda representative. Now either we use the axiom of choice, or no, anyway, we have to use axiom of choice to choose a lambda. So if you choose it one and for all, then we can sort of decompose any real non-standard real number. Okay, I will write again when necessary. We can decompose it the following way. So this a lambda will play the role of sort of basis, and the coefficients will be standard real. So it gives us some relation between standard and non-standard. Yeah, so we do it as follows. We take x in star r plus and write the following sequence. X0 equals x, lambda 0, lambda of x0. So it is the class where x0 is. C0 is standard part of x0 divided by a lambda 0, and s0 is 0. Then we write the next. X1 equals x0 minus c0 a lambda 0. So this we split from x0 its principal part. Yes, so what remainder is small, what x1 is small relative to x0. So if you divide x1 by x0, we will have something infinitesimal. Lambda 1 is lambda of x1. C1 equals standard part of x1 divided by a lambda 1 again, and s1 equals s0 plus c0 a lambda 0. So we subtract this term from x0 and add it to s0. Yes, and we will keep doing all the time, and so in the end here we will have 0, and here we have x0, and so on. X I plus 1 equals xi minus ci a lambda I. Lambda I plus 1 was lambda of x I plus 1. C I plus 1 is standard part of x I plus 1 divided by a lambda I plus 1, and s I plus 1 equals s I plus c I A lambda I, and so on. And then we reach the first ordinal as an index. Index is an ordinal. The first ordinal, first infinite ordinal omega, and we can jump to omega from the previous ones. Yes, so we define x, the set x ci lambda I less than omega is all y such that ci lambda I less than omega are the same as for x. Yeah? So this is a set of all non-standard numbers. It is in star R. We take a representative from this. It is called A. Ci lambda I less than omega in X. Ci lambda I less than omega. Yes? And then you define the term number omega. As omega equal A Ci lambda I less than omega. So it is sort of the sum of all the previous terms. X omega equals x minus s omega. Lambda omega is lambda of x omega. C omega equals standard part of x omega divided by A lambda omega. So this way we define the object at the step omega. Now we write the same. X omega plus 1 equals x omega minus c omega A lambda omega, and so on. Like this. So this way we reach the index to omega, then we jump in the same way over that index, and this way we can, if you have a successor ordinal, so which have the form previous plus 1, then we simply repeat this step. If you have a limit ordinal, then we jump to this limit ordinal, repeating this trick. And so, using the transfinite recursion, we do it for all ordinals up to what is necessary. So what is necessary? we every time we receive a different number xn. So the number xi plus 1 is always less than xi. So they don't repeat, and the set of such numbers cannot be more than the set of all non-standard numbers. So we have to take the ordinal. This means that this process will finish before we reach the ordinal, which is larger than the cardinal of all non-standard real numbers in this model. Yeah, so this is some quite definite set, some quite definite ordinal. So we have to write at every step that if x at some I is turned out to be 0, then the process is stopped, simply. Yeah, so this way the process will stop before we reach these larger ordinals. So this way we put in correspondence to the number x, we put in correspondence the sequence of lambda I, ci. No, xi and si are derivatives of this. I don't write it. Here I less than I0, where I0 is some sufficiently large ordinal. And this set lambda I is called spectrum of x. No, I call it spectrum of x. Why not? And we can also define a function f, say x of lambda, which looks as follows. It is ci if lambda I in the spectrum of x, 0 otherwise. Yeah. So it is a useful function. Now, we have here in our problem, we have two non-standard numbers for any point. We have its radius, rho, and the angle, phi. So phi belongs to star 0 to pi. Yeah. No. So let us start from. I'm sorry. Yes, star is here. So let us. If phi is not infinitesimal here, then phi. We have here lambda 1 are all the points, in fact, all the points all of our all the points of this set, but infinitesimally small point, no, or infinitesimally close to the to 2 pi. Yes. It is lambda, we started from x0 or x1, x0, lambda 0. equals 0 to pi star minus, I would say, more monad of 0. No, union monad of 2 pi. Yeah, so the points which are infinitesimally close to 0 and 2 pi. So this is the first, and all next sets will be simply infinitesimal or infinitesimals of different order in the real line. Yes, so lambda I in lambda, just of real line. Yeah, so this means that we can decompose the angle phi, the same way as we did it with any other number, and correspondingly we have the function f phi of lambda defined the same way. Okay? And this function is the most important for us. Now, what I'm going to do now is the following thing. I promised you to represent this space, asymptotic space, as a space of functions, functions like this, with a specific distance function. To this, so here we have the function which is defined on the space lambda. It is the set of equivalence classes of our function. We want now to somehow identify this set, the set of radii, where rho is changing, or at least with some factor set of it. To this end, let me introduce some other partition of real line. So we write that x, if x, y in star r, we write that x, like this, in this sense, equivalent to y, if model x minus y less than k, which is a standard number. Yeah. And again, R is, let me take R plus. R plus is partitioned into equivalence classes. So R star R plus, which is factor over this identity relation. Let me denote it by M. It is different. So that previous lambda was sort of multiplicative division, and this is additive division. Yes? It is like mu, and mu small element of this set. It is also an ordered set, and for any x, in star R, we denote mu of x such that x element of mu of x. Yeah? And so any point, any say rho in star R plus, I put in correspondence e to the power minus rho, also in star R plus. Yes? And if rho is element mu of rho, rho is element of this, and this is element of lambda of e minus rho. Yeah? I put in correspondence to this mu of rho, this lambda of e minus rho. Yeah. So this is true good one-to-one correspondence. And back. So it is so lambda of mu is mu of lambda. That's it. And now I construct a function g phi of mu the following way. Equals f phi of lambda of mu. Okay. This is so f phi. What is f phi? F phi of lambda equals ci if lambda equals lambda I in spec of phi 0 otherwise. Now all this is because we need the function e to the power minus phi 1 minus phi 2. One moment. Phi 1 minus phi 2 is e to the power phi capital. Yes, so we have here some inherent exponent. So here it is, this exponent. Now, this correspondence is the following. When lambda grows, yes, grows, then mu decreases. Yeah. Now, this function g phi of mu is a function such that it is not zero on some well-ordered set. Yeah? If you recall the process of decomposition of the function, of a number, yeah, then in this process, at every step we get a number which is smaller than at previous step. Yeah? So this means that lambdas go down. Lambda I plus 1 is always less than lambda I. Lambdas go down, and hence mu go up. Yeah? And the set where the value of the function g sub phi is not zero, this set is well ordered in this set mu. It is growing and well ordered. Why it is well ordered? Because this set is labeled monotonally growing and labeled by ordinals, and the set of ordinals less than some given ordinals is well ordered. It is the paragon of well ordered set. Yeah? So it is a well ordered set. Okay, and now let us return to our space. Yeah, we can define, we have epsilon. Let us define a function u of rho equals standard part of epsilon times rho. Now, where it is defined, so it is defined when epsilon times rho has a standard part. This means it is finite, bounded. If it is bounded, then we have this well-defined function. Otherwise, it is not defined. In fact, if epsilon is infinitesimally small, and then note that this function is defined, in fact, by on the set mu capital. Mu is defined on the set mu. Why? If, say, y1 in mu and y2 in mu, then y1 minus y2 less than some k in R plus, yeah? So y1 minus y2, and epsilon times y1 minus epsilon times y2 is infinitesimally small, yes, because it is an infinitesimal times bounded number. And so u of y1 equals standard part of this minus standard part of this of y1 minus u of y2 is 0. Let me write standard part of this equals 0, and hence u of y1 minus u of y2 is 0. This means that u is constant on each set of set mu. Yes, it is constant. No, if it is constant, then we can think that u is a function on the set of this sets mu small. The u is defined on the set M as a function on the set M. No, if the set M if its domain are elements of set M consisting of functions such that epsilon times these numbers are bounded. And now I formulate what's called theory. Standard part star D of rho 1 phi 1 rho 2 phi 2 standard part of this, so this is what we want to find, equals simply the following: u epsilon rho 1 minus epsilon rho plus epsilon rho 2 minus epsilon rho, where what is standard part? U of rho 1 minus U of rho U plus U of rho 2 minus U of Rho-Tweedle, yes, where U of rho is here. What is Rho-Tweedle? Is a number such that Rho-Tweedle mu-Tweedle, yes, first of all, and on mu-Tweedle we have this function, two functions, the function g sub phi1 and g sub phi2, yes, such that mu-Tweedle is the smallest mu in mu capital such that g phi1 of mu equal g phi2 of mu for all mu less than mu-Tweedle, and g phi1 of mu-Tweedle is different g phi2 of mu-Tweedle. So the function g phi1 is something like this. No, they can be positive and negative, and this is the mu axis. Yeah. And similarly, we have a function g phi2, yeah, something like this. It is equal the same, and here, for example, it is different. So this is mu-Tweedle. It is where the spectra of the numbers phi1 and phi2 first diverge. Why it is so? is so because if here is mu twiddle, so here we have a mu twiddle, and e to the power minus a mu twiddle is in lambda of e minus a mu twiddle. Yeah. And so this means that phi1 minus phi2 equals e minus times some bounded k. So this this difference of spectra gives us the estimate from below. So phi1 minus phi2 more than ce minus mu twiddle. And then so phi equals minus mu twiddle.
Minus or plus?
Excuse me?
Phi equal to mu tilde is plus. This one?
Plus. Mu twiddle. No, it is not mu twiddle, it's a mu twiddle. Phi is a sub mu twiddle. So it is element of this class mu twiddle. So, standard the epsilon of x1, x2 equals standard of maximum of epsilon rho 1 minus rho 2 epsilon rho 1 plus rho 2 minus 2 a Newton. Yes. One moment. Okay. Now, epsilon times a Newton equals u of Newton. In fact, equals rho Twiddle. Okay, so it is standard of maximum of epsilon rho 1 minus epsilon rho Twiddle, this, plus epsilon rho 2 minus epsilon rho Twiddle. Here. This is elementary equality. So, maximum of module A minus B and A plus B minus C, minus 2C. Maximum of this equals A minus C plus B minus C. Great. Now we have to consider different configurations of A, B, and C. say, suppose A more than B more than C. Then we have maximum B A plus B minus 2C. So this is A, this is B, A minus B. Just a minute. It is no, certainly equals A plus B minus 2C. So let us see. Suppose A more than B. So A minus B minus A minus B plus 2C equals to B minus 2C. So the difference depends on of course, A minus B minus A minus B minus 2B minus 2C. Yes, less than 0. Yes, here was a mistake. So if say A more than B more than C, then we just find the difference between this and this is negative. Yeah, so this means that this term is more. So maximum in this case is A plus B minus 2C. Yeah, so all in all we have 6 different combinations, 6 different say orders of the size of them, and I leave you to check it yourself that for all 6 cases we have that this maximum is this. One moment. Is it correct? A minus B. Yes, I think it is correct. I think it's correct. Yes. Okay. So what we found, this formula A minus C plus B minus C says the following. We have somehow transplanted the spectrum of the numbers phi 1 and phi 2 on the row line, yes, from the origin. Yeah? So here we have this spectrum. And the recipe is the following. We take the point where first these spectra become different, so they diverge somehow. And from here on, whatever they behave further, the fact that at some point they are different, either different lambda or mu or different c, then this point is rho twiddle, yeah, and from here on the lines diverge, yes, here it goes to some point x1, here it goes to some point x2, and the distance between these 2 points is found by the following form. We have first to go from x1 to this point x twiddle, and from x twiddle to x2. Yeah? So this is the distance from 0 to x1. It is rho 1, this is rho 2, and this is rho twiddle. Yeah? So we have this fork. This fork to happen, we need that at some distance these 2 geodesics or 2 radii are infinitesimally close. So they are infinitesimally close and then they diverge. So this is what happens. So we have a partial correspondence. We have a partial correspondence for any number x in star r plus. We found this function or this sequence lambda I ci. Yeah, and correspondingly we start f x of lambda from lambda to I. So it is a standard function with standard values, but with non-standard domain. Now the question is, yes, and what is said that the set spectrum of X is a well-ordered set. And we can consider the space F space of functions f of lambda such that f of lambda different 0 on a well-ordered set spec of I don't know what. And then we can define the distance between these two functions by the formula similar to what was previously. So the question is given a function f in our space, does there exist x in star r, no, plus, such that f equals fx? So, from the previous, we cannot conclude that such function exists because we did the opposite thing. We took a number x and then out of this number x constructed a function. Here we have to work in opposite direction. And this turns out that it is not always possible. So, in fact, we usually cannot. So, if what we did before could be called analysis of a number, spectral analysis of non-standard number, here we have a problem of spectral synthesis. Given some spectrum and the function ci on the spectrum of lambda I, we want to synthesize a number, non-standard number x, such that further analysis returns at the same object, the same spectrum. In general, it is not possible. And what can be done? We can return to basics and construct another model, a wider, extended model of our universe, such that this is possible in that model. Yes? But it is possible only for the spectra which are defined in the previous model. Yeah? So in the new model we can find other spectra such that we cannot synthesize that spectrum, so we have to extend it further. And therefore, it would be very fine and very beautiful if F with this space F were exactly the if starting from spectrum from the space F, we could find the asymptotic space of hyperbolic plane. Yes, but it does not go this way. We need a very large model, which is called saturated model. In the saturated model, this synthesis is always possible. But I think I will not manage to tell you about saturated models, as it requires more space and time. So we have to have the following situation. So our conclusion. Star H epsilon. Yes, so this is the asymptotic space. Can be isometrically embedded into the space F. One thing. The second thing, the model, let us call this model M. It is a non-standard model of our universe, of U. Can be extended to a larger model M prime containing N, such that star H epsilon M prime, so it is the extension of hyperbolic plane in the new model M prime. F can be isometrically embedded into star H epsilon M prime. So, we enlarge so that this space F can be embedded. For saturated models, star H epsilon is isometric to F. So, no, here I just claim, I don't prove it. It will require much longer time to prove that there exists models where these two spaces perfectly coincide. No, that's it. So I wanted to finish today. I wanted to say that the problem of description of asymptotic spaces is it is just example, simple example, which is already useful for different problems in analysis and geometry, but there exists much, I would say, trickier spaces, which is also important to find asymptotic space. It makes direct sense, for example, in some problems of fluid dynamics. So I personally keep working about this. So let's finish today.